Thanks a lot for the very nice introduction. First of all, I'd like to thank the organizers to give me this chance to introduce some of the recent works on the measurement device independent QKD. Okay, so today because this is a tutorial session, so I will use half of my PPT slides, half use the handwriting. And then if you have any questions, just feel free to interrupt and ask. First, I will give a brief introduction about the QKD. Here, I assume that most of you already know that's all the QKD protocols. So I will just give you a very quick review. And then I will talk a little bit more about the qubit encoding with optics, because from yesterday's talk, I can see that there were lots of the audience come from the CS background. Maybe you are not too familiar with those optics, so I will mention that. And then I will talk about the measurement device independent schemes, mainly about the recent developments on the twin field QKD. And this has been really the focus of the QKD in the past like 5 years or so. And then I will talk about our recent work on the mode pairing encoding. Okay. So basically, it's go back to the original true mode encoding. Finally, I give some conclusion and some of the open questions. Introduction. So in the QKD, there are three types. Mainly, there are three types of QKD systems. One is the prepared and measured, such as a BB84. Okay, Alice prepared a bunch of states, like 0, 1, plus, minus, sent to Bob. Bob randomly choose bases, X or Z bases, perform the measurement. Later on, they will compare the bases, and then they only keep the bits that they share the same basis. Okay. All right, so this is a kind of BB84. Okay, Alice is a source, Bob is a detection. Another type is we call the entangled distribution-based protocol, such as X91, BBM92. So here I will mainly introduce BBM92. So we have a source, entangled source in the middle, 0, 0, plus 1, 1. And then send one qubit to Alice, send another qubit to Bob. Alice and Bob, in this case, Alice-Bob positions, they are symmetric. So Alice will randomly choose X or Z bases, perform the measurement. Bob will do the same. And in this case, both Alice and Bob, they are detection, they are measurement site, and the source is in the middle. Actually, when we put it in the middle, we assume that the source can be untrusted. So the security does not depend on the, so if Alice Bob claim they reach some secure key, that conclusion does not depend on the physical implementation for this source. Final one is the reverse version of this entangled distribution protocol. So we call the entangled measurement-based protocol. So in this case, it's the other way around. Both Alice and Bob, they are source. So let's say Alice prepare 0, 1, plus, minus. Bob prepares 0, 1, plus, minus, this kind of BB84 state. And send Alice sends qubits in the middle. Bob sends the qubit to the middle measurement site. The middle measurement site will project these two qubits into one of the bell states. Okay, so basically it's kind of this measurement site will initially these two qubits, they are independent. This measurement site will correlate these two qubits together so that you can reach the security. In this case, we put the measurement site in the middle. So this is we call the measurement device independent. Okay, the security does not depend on the measurement site. Okay, so there are three types of protocols. Today I will mainly focus on this type of protocols. But in terms of security, I will talk about the second one, entangled distribution-based first, and then I will come back to this one. All right, so I will introduce a very old security proof by Rowe and Chang. So the main idea that is in the second picture, when source in the middle, 0, 0, plus 1, 1, EPL pair in the middle, and then send to Alice and Bob, and the Alice Bob perform the measurement, this protocol, okay? In Rowe-Chang security proof, they assume that Alice Bob, they have quantum computers. They can store the qubits and then perform very complicated joint kind of qubits operations. Okay, so the key idea is that the Alice Bob eventually try to get 0, 0 plus 1, 1. but because the channel is noisy, and also maybe the source, even the source is untrusted, they might get 0, 0, minus 1, 1, or 0, 1 plus minus 0, 1. And so there are errors. Because Alice gets qubits, Bob gets qubits, we can write this 2 qubit state into this Bell state, okay, Bell state. And then the key idea is to use the entanglement distillation, So basically the idea is that, okay, because Alice Bob, they get qubits, and then what they can do is they can do the bit error correction and the phase error correction. Eventually, they can correct all the errors. So as long as the state is not 0, 0 plus 1, 1, we call error. And then Alice Bob can do quantum error correction to correct all the errors to get this 0, 0 plus 1, 1. So that's the main idea of behind the low chop. And then we know that once Alice Bob gets 0, 0 plus 1, so basically almost pure EPR pairs, then it's almost pure EPR pairs. After this step, Alice and Bob, they perform local Z measurements, okay, sigma Z measurement, and then get the final key. It's not hard to show that for this state, because it's a pure state, for any Eve system, it's a tensor. It's a tensor with the Eve system, it's independent. And then perform the measurement, you will reach this ideal key, okay? So this is come from for this ideal keys come from the security definition by Bang-Or and Renato Renner, all those very early works. And also this security proof is equivalent to this, for example, recently like Renato Renner, they have a very fancy smooth mean entropy. It's essentially, it's a same, essentially you can reach to the same conclusion, okay? So that's the idea, okay? So this is a kind of the basic idea for this security proof is that you get a qubit, bunch of qubits, it could be noisy, and then you do some error correction, quantum error correction by some, with some LOCC communication, okay? Of course, in this case, we have a few problems. One problem is that the Edison and Bob, they need a quantum computer. We don't have a quantum computer at the moment. So what do? So there are a few steps we can reduce down to this, we call the preplanned meshed scheme. The first step is the source replacement. Okay, so this scheme, by the way, so in the very original papers, so they don't do it, we use these names, okay? So this is really like a very recent, not very recent work, like 10 years ago. It's 10 years after those works. I will use this modern terminology, okay? So first step is we can use the source replacement. It means that the classical encoding, you can treat it as the equivalent to say that it's an ancillary qubit plus control unitary, okay? What does that mean? It means that, okay, when you do this key encoding, okay, let's say you choose a basis, okay? When Alice chooses a basis, and then what we can do is that we can just do this classical control, like when you say you want to encode a 0 or 1, you can use this classical control. Okay, so that's what's happening. Okay, you flip a coin and then randomly choose a basis, and then flip another coin, randomly choose the key bit. Okay, for this one, it's equivalent to say we can do these quantum operations, and then you perform measurements. Okay, and then you perform measurement. It's equivalent. So basically, it's like we want to. So these two, they are equivalent. So it's like a classical encoding. You can use the source replacement with the kind of ancillary qubit plus control unitary. Okay, so that's the idea. Okay, another one is for this classical operation, for this quantum operation of the error correction. That step is the classically, so we want to replace those operations with the classical operations, classical post-processing. So because we don't have a quantum computer, we don't want to do this very complicated joint quantum error correction operations. So what we can do is that if you choose those quantum error correction code smartly, and then all those operations can be replaced by classical post-processing. Okay, so let me give you one example. Okay, suppose that's a circuit we need for quantum error correction. That's the key bit we need. Okay, for this operation, if this operation we can change the order of this operation and the measurement. Okay. So we replace this quantum operation with classical post-processing. this operation we call the classically replaceable operation. Okay, so this is very close to this we call the defacing incoherence operations. Okay, defacing incoherence operation. So essentially, they are essentially classical. You don't really need to do it in the quantum way. Okay, so that's operation side. So we have a source. In the source, we can replace entanglement with the classical controlled source. And in terms of operation, we can replace those fancy quantum operations with the classical post-processing. Okay, so that's the idea. And then we have short-scale secret proof. So basically, you replace all those complicated quantum operations with classical post-processing. You replace this entanglement source with the classical controlled source. So eventually, we get this famous short-scale formula. Okay, so eventually, the bit error correction becomes just a regular key reconciliation, like sometimes we call the error correction. Phase error correction becomes a privacy amplification. Okay, so that's the idea. Okay, so here I want to mention a little bit more about the one more step of the short Pascal secret proof. So this is we call the Gauss-Monroe-Leukemhouse Pascal's GLP framework. So the idea that in practice, sometimes we have a bunch of we call the good keys, and also we have a bunch of bad keys. Okay, so because of the device imperfection, okay, sometimes we have good keys mixing with the bad keys. The idea of this tagging idea is that if you have one bit of good key, XOR one bit of bad key, the outcome is good key. So think about that. Eve knows this bad key, but she does not know the good key. If you XOR them together, then the result Eve cannot know, right? So that's the idea. And then, so the result is that the results for this framework, for this tagging idea, that you don't really need to know that for this, after the measurement, you get a bunch of raw key. And then you don't really need to know that which bit they are secure, which bit they are good ones, which bits they are bad ones. As long as you know the amount of good keys, amount of bad keys, that's enough. Okay, so that's the idea. All right, so I will switch to the handwriting so that I can explain a little bit more on this one. And also I will mention about here so far what we talk about is always we talk about qubit. But in reality, we have to really use some physical system to encode and decode those qubits. Okay, then it comes with the optics. Okay, let me switch to the. All right. Okay, so one second. Okay, that because probably I will try it again. Okay. That's very strange. It works.
It worked earlier, right?
Yeah. It works. What if I do this again? Yeah, touch something. I didn't touch anything.
Oh, it's all connected. It seems like your machine is not sending a signal.
Is there? Oh, okay. I'll just probably there's some connection problem here somewhere. Okay, I'll be careful. Right, thanks. Sorry for the option. Okay. Okay, let me introduce some of the encoding. Okay, so really now we really want to encode this. Let me see. Okay, so any questions so far? Okay, any questions so far? So I quickly went through the those basics about the QKD security proof. All right, so now we want to encode a qubit. How can we encode a qubit? So first of all, I'd like to quickly introduce we call the optical mode. All right, so I know that many of you are quite familiar with the quantum optics, and some of you are not familiar. So I will just quickly go through it. So when we want to encode a qubit, so we want to call it a qubit. So normally we need to find like a two-dimensional Hilbert space. Then there's a qubit. Okay, so that's the idea. So in the optics, we need to find that. Okay, in quantum optics, we normally use let's say in the quantum mechanics, we use the second quantization to describe the state. For example, when we use a cat, okay, when I write down a cat, it means that it's a optical mode. Okay, so if I write down another cat, that's another optical mode. What this means? I can put photons in this cat. It's kind of pocket. It's kind of pocket. You can put photons in the pocket. Okay, so that's the idea. All right, so I can put, let's say, in this cat, I can put 0, 1, 2. Okay, depends on how many photons you have. You can put into this cat. Okay, so if I use this tensor, have another cat. Okay, I can put other photons in another pocket. So that's the idea. So in this talk, when I talk about the optical mode, they are all orthogonal. Orthogonal means that if I put a photon in this pocket, okay, think about that. If I put a photon in my pocket, or if I put a photon in your pocket, these two photons, they are different. You can tell the difference. Okay, you can tell the difference. Okay, and then but in general that's not true. In general, not. So this is what we call the orthogonal mode. Orthogonal mode. But in general, that's not true. Okay, in general. So think about that. So when I have $1, you have $1. So that's totally different. Okay, you can use your own dollar. I can use mine. So there's no connection at all. But think about that. Think about that. Okay, probably. Think about that. If I have $1 in my pocket, and that dollar, actually, strictly speaking, it's not really belongs to me. For example, if you really combine, if you really think about another pocket in my wife's pocket, then it's not totally independent because we share this dollar. Okay, so that means that for optical mode they can be, it's not necessary to orthogonal. Okay, even you have a true optical mode, they can be, you can have some overlap. Okay, think about that. Okay, let me consider a case. Okay, so something like this. Okay, so in the temporal domain, in the time domain, you can have some overlap between two optical modes. But in this talk, I will talk about all the modes I talk about. They are all orthogonal. So when you have a photon in this mode, it's perfectly distinguishable with the another mode. Okay. For optical mode, we also have a lot of restrictions. Like for example, essentially it's just like you cannot create information. You cannot delete information. This kind of principles. We have, of course, we do have a full course for the quantum optics. We do have experts like Norbert and Professor Krat. They will tell you lots of rules about this optics. But in this case, I will make it very, very simple. Okay, so in principle, how can we do the encoding then? So one way to encode is that so suppose this is in time domain. If I find the two locations, they are far away from each other, then we can think of these two locations, these two optical modes, they are orthogonal. They're orthogonal. So then we can define a qubit subspace. Okay, so suppose I have so I have two optical modes. So suppose I have one photon here, no photon here. So that means I can write down this way, or I can have another state, 0 photon in the first mode. One photon in the second mode. And then I can also have a superposition of these two states, some of these. minus like something like this. Okay. Keep in mind that sometimes people ask that okay, for states like this one, where's the photon? Okay, actually the photon states like this one, photon is in the first place and the second place simultaneously. Okay, so this is in the superposition. Okay, so this is something we use a lot in the QKD encoding. So this we call this called time being. Okay, later on I will add a phase. Okay, phase encoding. Okay, time being phase encoding. Okay, so this is the qubit. This is a qubit subspace. Okay, so think about that as 1, 0 will be our logical 0. 0, 1 will be our logical 1. Okay, qubit 0, qubit 1. Okay, and then if you want to add like qubit, so this is the 0 and the 1. And if you want to say what's a plus or minus, then you add a phase here. You can add extra phases here. Okay, so this is a very popular encoding scheme in the QKD. All right. Okay. Any questions? Any questions? Optical mode. Okay. I will use that later on. Okay. And then for this time being, okay, it's not necessarily time being, right? Okay, so here I just gave one example. If you use some other degrees of freedom, like you can use a polarization. You can also use the let's say you can use a spectral mode. You can use the even the optical angular momentum mode. So basically, any optical mode you can use, orthogonal optical mode you can use it to construct this qubit subspace. Okay, and then you can use it for the QKD encoding. Okay. All right. So let's go back to BB84. Then how can we use this optical mode to do the encoding? So Alice will just prepare 2 optical pulse. And then one way to do that is like, okay, again, so think about that. This is very similar to this picture. And then she will use S. I will just label it with the mode S, mode R. It stands for the signal and the reference, okay? All right, so she will have this one, S and R. And then ideally, Alice will send out just one single photon state, just one photon. And then so she will say that the photon is in the superposition of the S and R. Okay. And then she can encode some phase between them. Okay. So basically, sorry, the other way around. So I think okay, HBI theta. Okay. Think about that. The phase is only applied to the signal pulse. Okay, and then I get this one because for this one I don't have any photon. I don't have any photon to pick up the phase. So the overall phase, the phase term is always 1. And then for this one, I have 1 photon in the signal mode, so I can pick up a phase. I can pick up a phase. Okay, so that's the phase encoding. Okay, this is phase encoding, and then we can choose the theta to be 0, half of pi, 3 pi over 2. Okay, and then this is we call it the x and the y basis. Okay, x and the y basis. All right. All right. Of course, this is ideal. This ideal case. This is the ideal qubit. So everything is good. So, but in reality, we do not. At least we don't in the lab. We don't have the single photon state. So what we have is we have a coherent state. Okay, coherent state is a little bit more complicated. So the state is a superposition of all the Fock states, all the photon number states. Okay, so it's the like this one. Okay, it's a little bit complicated, but let me see. So for this one, it looks a little bit complicated. It's okay, sorry. Okay, so this means that in this mode we have k photons. So this is we call the coherent state. For the coherent state, we have 2. So for alpha, it's normally a complex number. So we can write down as like it's intensity square root of intensity times e to the I theta. You can also have a theta here. So that's the state we use a lot for the encoding. Okay, for the encoding. Then if we also use this one, and interestingly, it's like we have a coherent state. Let's say we have a coherent state in the S. We have a coherent state in the R mode. And then when you do the encoding, what you will get? So for this fourth state becomes if it's 0, then it's alpha. If it's half pi, then I alpha minus alpha minus I alpha. Okay, so this is corresponding to this theta equals to 0, half of pi, 3 pi over 2, something like this. Okay. All right, so that's the encoding. Then from here, you can quickly check that then for this kind of encoding, it's not perfectly qubits encoding, because there will be some overlap between the 0 state and the 1 state, etc. Okay, so in order to make in our analysis, we normally make it simple. That's okay. So let's assume that alpha mu is small enough, then it's approximate to be single photon qubits. Okay, qubits is okay. Let me see. That's the okay. All right. So I really need to draw this diagram. Okay. So okay, first step we need to do is that we need to randomize the phase. So basically, we want to randomize this theta, randomize this phase. How can we randomize the phase? Okay, so we assume that there's a random number. Okay, let's say d-dimensional random number, and then based on this d, and then we put a random phase on this alpha. And then, so if you measure this, directly measure this in the computational basis, it will tell you that okay, what's the phase? Okay, let's assume that the result will be 0, 1, 2, d minus 1, and then this phase condition on what's the measurement result. Let's say I'll denote as I, and then this is the 2 pi over d times I, and then we will have phase x on the this coherent state. Okay. Okay. So here I will just mention that okay, if we perform, instead of for the first qubit, instead of perform, so this is a source replacement. Instead of perform this measurement directly, if you replace this measurement, we call the Fourier transformation first, and then perform the measurement. You will see that this result, the measurement result, will give you the Fock state number. Okay, it will give you a measurement result of k. This k will give you this. This k is the photon number in this Fock state. Okay, and then what we can do is that's the. So let's say Alice do the encoding. Alice can randomly control this phase and then do Fourier transformation on this random control, and then measurement outcome gets k. When k is equals 1, then that's single photon state. That's the ideal case what we need. Okay, so this is the ideal case we need. Okay, for the rest, if k equals to 1, that's good. That's single photon state. And then, of course, there will be other cases like k equals 2, 3, like multiphotons. They can just throw it away. So throw it away. But of course, in reality, Alice cannot perform this measurement. But what they can do is that Alice Bob can estimate how many single photon states they send out. So this is the GOP I mentioned. That's the. So all they need to know is that the amount, the ratio of the single photon state. Okay, which as long as they can estimate the ratio of the single photon state, they can really they can really, because the GOP say that all you need to know is that what's the amount of qubits you have. All the rest garbage you can just throw it away. and then you can perform the secure key. Okay, so that's the ratio. Is the key point for the key parameter for the GLP, and then that's what we use we call it the coincident method. Okay. All right. So that finishes the original encoding. Okay, original encoding. All right. Okay, now I want to mention a little bit about what's the efficiency for this kind of encoding? What's the efficiency for this kind of encoding? Okay, let's talk about the picture. That's the Alice, Bob. Okay, so if Alice sends out 1 photon to Bob, Bob gets a click. The probability for Bob to get a click, we denote it as eta. So this is the transmittance. Alice sends out 1 photon. And then what's the probability for Bob to get a click? So that's eta. Okay, that's what we call the transmittance. Okay. All right. So now we want to check out for this encoding, what kind of what's the order of magnitude for this for the key rate? Okay, Alice encode kind of a single photons in 2 pulses, and the Bob basically just want to measure the relative phase between these 2 pulses. And then what Bob can do is that Bob can make these 2 pulses. Hang on a second. Let me go down. Okay, Bob will separate these 2 RNS, and then do the interference, perform the measurement. Okay, perform the measurement. And then as long as there's 1 photon reaches Bob's side, Bob will have a click. Whenever Bob has a click, they will get 1 bit of raw key. So for this one, the key rate is in the order of eta. So the probability for Bob to get a click is in the order of eta. Okay, it's O eta. All right. Okay. So now we want to move on to the MDI, this picture. So Alice and Bob, they both prepare this kind of state. Yes and no. And then they will do the interference. Okay, they will do the interference. Okay. So this R pulse will interfere with R pulse. Signal pulse will interfere with the signal pulse. And then in this case, let's quickly check out what's the probability for Alice Bob to get 1 raw bit. So because the total transmittance from Alice to Bob, the total transmittance is eta. Then let's assume that the measurement site is in the middle. Then this side, the transmittance is square root of eta. This side is also square root of eta. Okay. And but in this case, so if you look at the R, pulse of R to get a click, what's the probability for this pulse? Okay, suppose I have 1 photon in this in this mode to get a click here. It's the probability is square root of eta, right? Because I think about that, I have 1 photon here or here. It's in the superposition, okay, in the superposition. And then you send it to the middle and then you perform the measurement. So then the probability to get a click is a square root of eta. Similarly, for the if you have a photon in the signal mode, it's also square root of eta. So in the total, it's all, eventually we still get the O eta of the detection probability. So we can see that the key rate of this for this we call the phase encoding MDI QED is the same as the previous like BB84 encoding, prependent measured encoding. Okay. Any questions here? Any questions? Okay. So the key point is now I have 2 pulses because I needed two pulses to encode the information. Okay. So Alice encoded information that into the relative phase of these 2 pulses. Bob encoded information of the relative phase of these 2 pulses. When they send in the middle, perform the measurement for the Bell state measurement. The first, let's say, mode R, we need a click. Mode S, we need a click. And then we need a coincidence click. So that's why it's each one we have is square root of eta. Finally, we get the O eta. Okay. Any questions? It's clear enough, right? Okay. Okay, so when we get this one, so we can see that's the key rates of this MDI QKD, like this way. Or we just directly send the signal from Alice to Bob. It's the same, because in total, although in the first picture we only need to have click of one photon, in the second picture we need the detection of the two photons simultaneously. Okay. Now I want to switch back to the PPT a little bit because I cannot draw this diagram too well. Okay. All right. All right, so let me just quickly review this one, these two. I just explained that that's the, first of all, it's like we have, with phase randomization, we can have Fock state. Basically, we can measure in principle, we can measure the photon numbers. Okay, think about that as a source replacement picture. Okay, so the phase randomization is the key for the Fock state to appear. Okay, optical encoding, and then what do we explain? It's a time beam phase encoding, and again, it's not necessarily time beam. It can be any two orthogonal mode. Okay, I can use those previous encoding. Okay, and then we can encode this kind of BBA4 state. And this is what I just explained. Okay, Alice encoded her information into the relative phase between the mode R and the mode S, and then send to Bob. Bob do the interference and perform the measurement. So eventually we can get the O eta of the efficiency. Okay, for the measurement device independent QKD, let me mention a little bit of the background. So why we need this kind of an MDI QKD? The key point is if you think about this, for QKD systems, we have normally we have a source, we have detection, we have a measurement. Normally, detectors are much more complicated than the source. And for MDI QKD, the good thing is that both Alice and Bob, they have sources. And then the measurement site is put in the middle. It's untrusted. It's on the untrusted site. So in this case, all they need to, so in terms of security, Alice, Bob, all they need to trust is the source. And also for these two source boxes, they don't receive any signals. Okay, then it's much harder for the Eve to manipulate the inside the devices. But if you think about this, for the measurement device, you always receive signals from the channel. In practical scenarios, you cannot be sure what kind of signals you received from the channel. So that's why normally measurement device is more we have more loopholes than the source. So the MDI basically, it's the MDI QKD basically solve the measurement security issues, and then leave all the securities on the source side. Okay. And then so this is the time beam phase encoding I mentioned. Okay, let me do it again. So this is the So Alice, let's think about that. For the moment, let's assume this is single photon qubit, single photon source. Okay, you send us single photon and separate into two mode, and then the photon will be in this mode R or in the mode S, and then your encoding is on this one. Okay, you encode the relative phase. Okay, 0, half pi, 3 pi over 2. Okay, so that's the Alice encoding. So this is kind of in the qubit subspace, and then you have 4 BBA4 states. Same for Bob, single photon coming in, and then you do the encoding. Okay, and then you send to the middle. R interfere with R. S interfere with S, and then you have this kind of interference measurement is essentially is equivalent to the biosolidarity measurement. So it's like in the beginning I mentioned that the Alice prepare a qubit, Bob prepares a qubit, sent to the middle, and the middle site will project the 2 qubits into the one of the 4 biostates. Okay, so that's the idea. So this is the idea of this time beam encoding. Okay. So far it's still background. I haven't really reached the key point of this talk yet. Okay. Right, so I'll speed up a little bit. Any questions so far? Okay. All right. So first, okay. So this appeared in the earlier papers. Okay. But if you really look at very closely on this picture, okay. If you look at Alice, Alice encodes her information here, right? Bob encodes information here. So basically, you just add faces to this faces to the S mode. You add faces on the S mode, right? If you think about that, this R, this R channel is independent of the qubit information, right? So when I say qubit information, think about it, it's the 0, 1, plus, minus. It's independent, right? No matter which qubit Alice chooses or Bob chooses, this one does not change, right? All your encoding happens here, right? I'm not sure if I make this point clear. Okay, if you look at this picture, okay, again, so this is a very typical time beam phase encoding. Okay, I call it time beam because it's kind of two channels. I separate these two modes, okay, into two channels. You can combine them back together and then separate them in a time beam. Okay, so but this picture is, I think, is clear. All right, so there are two modes here, R and S. R does not receive any encoding. The only encoding you have is S. So if you really think about this picture very carefully, then I can, in principle, I can remove this red channel. Right? I don't need this red channel because it's independent of my encoding. Right? Okay, then if I remove this top red channel, what's the advantage I have? Because when we just calculate what's the efficiency for this one, it says that, okay, for this channel to have a click, your efficiency is the square root of eta. For this channel to have a click, your efficiency also is a square root of eta, right? And then I need a coincidence click. That's why square root of eta times square root of eta, you get this eta, right? But if I can remove the top one, all I need is have a click here. So my efficiency increased to square root of eta. Okay, think about it. Eta is a very small number. It's exponentially decrease with the channel distance. Okay, think about that, the fiber distance. Okay, eta is a very small number. Of course, square root of eta is much bigger than the eta, right? Okay, I'm not sure if make this point clear. Okay, so that's the idea of the okay, so we already do this calculation, and then we get for regular MD activity, we get the O eta. And then that's the idea of the twin field QPD. But of course, the original in the paper, they didn't put there in this way, but that's essentially the idea. So basically, it's like you can reach the key rate of the O square root of eta. But if you think about this, it's already in the previous picture. Okay, it's already in the previous picture. Okay. Right. Any questions? Any questions? Okay, so basically, if I remove I have two parts. One is the reference, one is signal. If I remove the reference part, what do I get? I get this picture, right? Okay, so what kind of encoding we have? So Alice will prepare some states, and then you put some face here. Bob will prepare some states, put some face here, send to the middle, perform the measurement. Interestingly, this protocol is already appeared a long time ago. It's like 2013 in the Agnes Francis thesis in the chapter 7. Okay, so who is PhD student of Norbert. And then when we talk about a few years back, like 2018, when I discussed with Norbert about this protocol, Norbert say that so originally, so in this thesis, they treated this one as like they call the MDI B92 protocol. So they think that's at that time, I probably Norbert can correct me, but at that time they think that this protocol is not important. It's not very attractive. That's why they didn't even, okay, they just put it in the thesis, not even in the publication. And then when we eventually we saw this twin field QED, Norbert comment on this one, say that he shoots his leg on this one. You can see that everything is already here. The key point that's we really need to work out this interference, and then there are a few tricks. the key point that's which is not appeared in this thesis is that they didn't apply the decoy state. They didn't apply the decoy state. Then you cannot estimate the good state well. Okay. So all you need to do is that it's original this N2 protocol plus the decoy state. That's this we of course when you perform the decoy state, we have to use we have to randomize the phase. Whenever you randomize the phase, you have to match the phase, because otherwise if you put a random phase here, that random phase will destroy your phase encoding, right? So later on, Alice Bob, they need to announce this phase and then match those phases together so that they can read out this original encoding. Okay, so there's one more step. Of course, there's one more step above this MDI B92. But if you look at the picture, the essential idea is already there. Okay. All right. Any questions? Any questions on this one? Okay. So you can see that's it's just very small idea and then you just miss it. Okay. It's really there. Okay. So here I will just put it in the secure proof in this picture. So this is a typical source replacement picture. Okay. So whenever you have a decoy state, then I need to do the intensity modulation. I also have a qubit subspace. Like again, it's a phase encoding. This intensity is for the decoy state. I also, in order to have this fork state, I need the discrete phase randomization. There are a few key steps. One of the non-trivial steps is that because this discrete phase S-Bob, they need to compare the phases and then select out the phase when they choose the same random phase. This step is incompatible with the fork state measurement, as I introduced in the handwriting. In the decoy state, we need the fork state. This K. I needed the photon number. It's incompatible. The key point to this incompatibility is that actually when we compare the phase, we don't really need to know each phase. All we need to know is that the phase difference of these two discrete random phase. Okay, and then the phase difference and the total photon number, they are compatible. So I can measure the total phase. I can measure the relative phase and the total photon number simultaneously. Okay, so that's the key trick we need to play for this source replacement scheme. But essentially, then without this point, otherwise it's essentially the same as the previous BB84 decoy state security proof. Okay. All right, so eventually we can okay. So a little bit there were a bunch of details, but eventually we can get the key rate of the O squared theta. Okay. There are also other security approaches for this one. Okay. So that's a big improvement in this QPD. Okay. And then there are lots of experimental realizations, okay, over the world, okay, for this scheme, because we can really extend the distances, okay, okay, almost double the distance. All right. So, but there's a big challenge in the experiment. So let me put it this way, because originally I have 2 channels, and then all I need is like the information encoded in the relative phase. So basically, like I have 2 pulses, and then the qubit information is encoded in the relative phase of these 2 pulses. But now I remove the reference. I only have signal mode left. Then that's a picture. So Alice encode a phase here. Maybe this Alice Bob, they are kind of hundreds of kilometers away. And then Alice encode some phase here. Bob encodes some phase here. These 2, they are independent lasers. And then they send it to the middle, to the interference. This interference should be able to read out the phase difference originally encoded by Alice Bob. So for this one, Alice Bob, they need essentially for this kind of system, they need we call the global phase locking. You really need to lock Alice Bob's lasers, and then you can really read out the phase. So this in general is this in general is a very hard problem. So think about that. We know that the phase of a laser changes very, very fast, right? So in terms of time, then is typically like it's the 10 to the 14 hertz, right? So 1 second you will change the phase like 10 to 14 periods, right? So if you really want to encode like half of pi, like pi on this optical mode, that's kind of, you have to really make sure that the channel won't change, and also the laser won't change the phase much, right? So so we did a little bit kind of a quick calculation on this one. So for hundreds of kilometers, you cannot change the during this experiment, you cannot change the fiber like 200 nanometers. So this is very hard. Of course, we have done this. We have done this in physics in the labs, for example, here at NIST. So we have those very precise time synchronization. Right? So essentially, what they need is this phase locking. Okay, but that's a little bit okay. We can do that, but this is very, very hard for experiment. Okay. All right, so we also have some bunch of the experimental demonstrations, and then we put some laser injection technique and plus some phase post-selection technique. But for the laser injection technique, some would argue say that you might introduce other loopholes. I'll skip the details. So that's there are a bunch of there are a bunch of this we call the very extreme experimental distance, like go to the 800 kilometers, like even over 1,000 kilometers. But I have to emphasize that for this kind of distance, it's just the proof of principle demonstration. They didn't really work out the finite size effect. Okay. So at the moment, with finite size effect, we can reach like 800 kilometers. But still, that's a limit. That's a limit we can do in the next round. Okay. So here, what's the problem? What's the big problem? The big problem is that I really need a global phase locking. That's very hard for experiment, unless you really you can have really very, very nice laser, and then you can really lock it. And then that's normally it's very hard. On the other hand, if I use two mode, it's easier because I only need to stabilize this relative phase of this very close by two pulses. But for that one, like a regular time being phase encoding, then I have the key rates of O eta. I don't have the quadratic improvement. How can we enjoy both? Okay, so that's kind of the trade-off between the practicality and the performance. Okay. So in order to for like schemes like twin field QKD, phase matching QKD, we have quadratic key improvement, but we need a global phase locking. But for the original time being phase encoding, it's easy because relative phase we need to stabilize the relative phase, but the key rate is linearly depends on the transmitters. So can we combine the advantage of both? Okay. It turned out yes, we can. Okay. Again, let's look at the original this picture. Okay, as I said, I can put these two modes together as separate in the time domain. Okay, separate in the time domain. Okay, we can do this one. All right. So if we look at this picture, it means that okay, I send out two pulses and encode the qubit information in the relative phase, and then I need the click here, click here. Okay, so that's why in the end, for this scheme, I have O eta. Okay. But the key point is for this encoding, so basically when Alice performs the encoding, these two optical modes, they are fixed in time domain. Okay, it's here and here. What if Alice used because Bob's encoding is exactly the same as Bob. So sorry, Bob's encoding is exactly the same as Alice. So I will just talk about Alice. Okay, so if Alice does not really fix these two pulses in the beginning. Instead, she encoded IID phases, IID encoding on all the optical pulses. And then after this click, they can pair all the clicks together. And then you can still use the relative phase to do the encoding. But because the original position is not fixed, then the scaling will be, later on we will see that can reach the square root of eta. So that's the idea of the mode pairing. Okay. All right. So this mode pairing is we use this for this mode pairing we use the IID encoding. So basically all the pulses originally, so these two pulses, we put these two pulses together. So this is one signal. This is another signal. But in this case, it's like for each pulse, you do the IID encoding, phase encoding, and then the measurement site will tell you that, okay, I have a click here, I have randomly, okay, and then I have clicks here. The rest, they are get lost. How do you do this mode pairing? It's like once you get a click, you wait until the next click, and then you pair these two clicks together, and then calculate the relative phase of these two encoding pulses, and then use this one as your encoding. Because this is a relative encoding, so we can see that this relative phase is relatively easier to stabilize in the experiment. But because I can wait until the next click to appear, then the click probability is square root of eta. Okay, I'm not sure if it is clear. Any questions here? So I can, yeah, we have a question.
Sorry. So even though your encoding was initially IID, when you sort of are trying to wait for the next click, doesn't that break the IID structure? So I'm not sure how the thing works the same way.
Okay, so but think about that. Actually, it's a little bit more complicated, and that's a very good question, especially in the security proof. That's a very good question. That's the hard part. Okay, what's the intuition behind it? First of all, you do the encoding all IID, and then when you perform the measurement, think about that. The measurement is performed by adversary. Okay, because she gets the IID pulses, all the pulses, they are the same. Then basically this measurement cannot really tell the difference of this pulse, these two pulses. So essentially you can claim that all the detection results, they are also IID. That's kind of the idea. Okay. But actually it's a little bit more complicated than that. Of course, you can really make this correlation of all the clicks, but that won't affect the security. Okay. But that's a very good question.
Thanks.
Okay. All right. Okay. So then we can see that's the okay. So here normally we also want to restrict that so when you have a click, you wait for the second click. You want to have a restriction that's how long you want to wait. Otherwise, if it's too long, then the phase might drift away. So basically, that's the how many pulses I want to wait. That's the number we put in the L for the L. Okay. From here, you can see that when L is equals to 1,000,000, then it's very close to the original PMQD. Okay. There's kind of like a one mode, like without phase locking, without the global phase locking this scheme. Okay, hang on a second. Okay, so there are also other security analysis for this one. Okay, so but they eventually the result is similar. It's also the square root of eta. And then we also have the experimental bunch of experimental demonstrations for this one, and then there's also another experimental demonstration, and then I assume that the Zhou will talk about that sometime later. Okay, in this conference. Okay, okay. Any questions so far? Okay, any questions so far? Okay, 10 minutes left. Okay, I will talk about the open questions on this topic. All right. So what's the features of the mode pairing scheme? Later on, we will see that actually the optimal intensity will be higher than twin field QPD. And then so that means that in the short distances, the mode pairing scheme will be we will yield a higher key rate. Okay, so so this is already implied in the very original this MDI B92 this protocol. If you look at this Atkins thesis, okay, so over there they analyze the attacks from the for this B92 protocol. From those attacks, you can see that the Edison Bob, they have to use a very, very low intensity to make sure that Eve cannot really distinguish the different phases encoding of the like alpha and minus alpha. From there, you can see that the intensity cannot be too high. Typical number is like intensity is in the order of like 0.05, like 0.05 photon per pulse. Okay, but with this true mode encoding, for this true mode encoding, we optimize the scheme. We can see that for this one, optimal intensity will be in the order of 1. Actually, it's a 0.5. Okay, it's 1 order higher than the original this twin field QKD. We can see that the key rate will be higher. But the shifting factor is worse. Shifting factor means that because you do the IID encoding, and then you want to, because it's a phase is IID, then you really want to have 2 pulses. They have the phase difference is 0 or pi. Then so the shifting factor is normally quite bad in this case. Okay, in this case, and also you need to match the intensity, etc. So because this IID encoding, and then before it's like these 2 pulses is fixed, you know what kind of intensity you want to put in these 2 pulses, and what kind of overall phase you want to put in these 2 pulses. But now because you have to post-select those phase and the intensity information, then the shifting factor is also worse. The good thing is that the key bit and the basis value is determined in the post-processing. So this is different from the regular QKD. Normally in the QKD, for the QKD protocols, Alice, normally she will determine which basis she want to use, and then she will directly get what's the bit value or basis value. But in this case, both bit and the basis value, they are determined in the post-processing after the measurement site announces the click, Alice Bob will pair the pulses together and then tell what's the bit, what's the basis. Okay. So of course, this is a big challenge for the security proof. And I put all the schemes in this picture, so we can see that in the very original current BB84, the performance is very bad. So we can show that actually in the very early novice paper show that So this scaling is the O eta square. With the decoy state, we can improve to the O eta, and also we have the information security improvement. Like the source is more secure in a sense. So this scaling is a little bit arbitrary. Okay, and then with the MDIQD, the scaling is still O eta. But the security, information security is much better than the regular decoy state BB84, because I solved in this MDI, we solved the measurement problem. Okay. Here we need to charge both measurements and the source. Here we only need to charge the source. Source very easy. And then we have a big improvement of the twin field QKD, go from the O eta to the O squared of eta. And then for the mode pairing, we improve the performance a little bit. The key point for this for mode pairing is that we have the implementation practicality. We increase it quite a bit. So we, instead of use the we call the absolute phase to carry the information, we still use the relative phase to carry the information. So that we don't need to really need to lock the independent laser, the phase of the independent lasers. So that makes the experiment much easier. Okay, there are a bunch of questions left. The first question is that because the shifting factor is too bad, can we have better pairing strategy? Especially so that because shifting factor is bad, then especially in the X basis, the fluctuation will be very, very bad because the data, the number of data, the valid data will be very small. So there are a few ways to improve this pairing strategy. So currently, what we do is that we find the first click, we wait the next click, pair them together. Find the first click, and then wait until the next click. Okay. Even for this picture, you can see that maybe it's better we pair these 2 clicks together and then pair these 2 clicks together. Okay. Depends on how you view it. And also, when we do the pairing in the security analysis, we assume that Alice Bob do not use any phase information or intensity information. But if they can use this phase and some phase and intensity information, they can do this shifting factor much better. Okay, how can we improve this one? So can we develop some pairing strategy that depends on the phase and the intensity information? Of course, this pairing cannot reveal any key information. Okay, the encoding key, you cannot reveal it. Okay, so this is a kind of a big challenge right now. So if we can improve this pairing strategy, then we can really increase the X-space data, and we can improve the shifting factor and improve the finite size effect. But the point is the security proof is a little bit tricky at this point. We don't have much of freedom here. Okay, and also ideally, can we separate the key generation and the test bit so that we can get the better shifting factor. Finally, one final kind of point for this one is like maybe we can for this one, because of this shifting factor is bad for the first short distances. Regular MDI phase encoding QPD is better than this mode pairing. Can we combine these two together? So basically, all we can do is like we just do regular MDI phase encoding QPD, like two parts. And then if both of them click, I will just say that for those data, you will just go through this regular MDI QPD. But many cases, okay, for many cases, for these two pulses, only one clicks. The other one does not click. For those pulses, can I pair those single clicks together? So that's for their part, I can use the mode pairing to kind of recycle those single clicks. Originally, I need a coincidence click. Now, for those single clicks, can I recycle those single clicks so that I can improve the key rate? For that case, then we know that if I can combine these two together, then obviously this protocol is it's better than the regular, always better than the regular MDI QPD, right? So that we can improve the key rate. And so this is also, we need to work out this pairing, how this security, the pairing strategy, how this pairing strategy adapt to the security proof. There are a bunch of other questions. In terms of experiments, we can go beyond the time being mode. What we can do is like, for example, for some optical labs, they can play with the frequency domain, spatial domain, optical angular moment. So basically, it's like you can use all the degrees of freedoms. Basically, as long as you use other degrees of freedoms, essentially those are the different channels. I can also pair those different channels together and then look at the relative phase for this one. I think the hard part is that how can I encode phases, like encode my qubit information efficiently to those kind of different kind of degrees of freedoms, and then so that I can use many channels simultaneously. And also we can apply the similar idea to the continuous variable QPD. Actually, even for the twin field QPD, you can another way to understand the twin field QPD is like go from the phase matching QPD is like you go from the continuous variable kind of point of view. Okay, I will skip that. And can we have more untrusted node in between? But we don't really want to use the quantum memory, like a repeater, those fancy tools. But we can reach like the key rate over square root of eta. Is that possible? Okay, we add more node in between, and then can we do even better? Okay, so practical. It's kind of a practical repeaters. Okay, so that's the conclusion remark. So it's like finally we reach the key rate of the O square root of eta. But we don't really need this global phase locking. So from the experimental side, it's easier. But still, we have lots of problems left. Okay. So before I jump to the final slides, I need to do some advertisements on this Journal of the Electronics. I think the key point that I want to give is like this. They have a special issues for the quantum information computation and the cryptography. You are welcome to submit the works. With that, thank you. Any questions? Yeah.
Okay, we got questions.
Hi, it's Jan Krause from Fraunhofer HHI. So my question is, as I understand it, currently Alice and Bob are using a phase randomization for each pulse with a complete uniform phase out of 0 to 2 pi. Do you think it might be beneficial to use a discrete, and then this small sifting factor probably results from only using those pulses where the phase difference or yeah, what's very close to 0 or a pi or so on.
Okay, that's a very good question. Actually,
the question is actually, do you think it might be beneficial to use a discrete phase randomization and then have a better sifting factor by taking these deficiencies into account?
Okay, that's a very good question. Actually, that's exactly what we are doing. So instead of, we don't do it like when we do the phase randomization, we don't do it continuously. Otherwise, if we do it continuously, then the sifting factor will go down to 0. So what we do is like we use a discrete phase, like a D is typically, let's say 16, 12 in the number of the 16 and 12. And then you can prove that this is already good enough when the alpha is not too big. Think about that, so alpha is in the order of 0.5, square root of 0.5. Then if we choose like a 12 discrete phase, that's already sufficient. And then when you measure the Fock state, that Fock state, K Fock state, we call the pseudo Fock state, is very close to the, it's already very close to the real Fock state. Yeah, that's very good question. Yeah.
Thank you very much for the very nice talk. My question is also related to the phase randomization. So my understanding is that the current finite key security proofs for the co-state QKD need to assume continuous phase randomization. Okay. However, I saw that you presented some finite key results for the mode pairing QKD. However, now you said that you use discrete phase randomization. So my question is how you managed to overcome that issue.
Actually, we do have another work, say that's the okay. For this core state, you don't really need to do this continuous phase randomization. Discrete phase randomization is sufficient. So so basically, if you choose the phases, okay, as I just explained that. So when alpha is in the order of square root of 0.5, if you choose, let's say 16 discrete phases, you won't. It will change the key rate a little bit, but that's too small. You won't even see it.
Yeah, but my understanding is that the paper that proved that considered only the asymptotic regime. So I haven't seen any the co-state finite size security analysis that consider discrete phase randomization. Okay. So my question is about the graphs that you presented with finite size effects. Mm-hmm.
Okay. Yeah, some others. Okay.
No, I don't think it's this one. I think it's later. Here. Okay. My question is whether these results take into account the fact that you use discrete phase randomization rather than continuous.
All right. So actually, if you use, as I said, if you use phase like 16 phases, that part, it won't affect this key rate at all. Because the thing about that's the key point, the key question we want to really check is that how this K Fock state, if I use like discrete phase randomization, how this when I say K Fock state, it's different from the real K Fock state. The trace distance of these two states is too small. Let's say I'm talking about 10 to the like minus 40, minus 30. It won't affect because if you add this 10 to the minus 40 to your phase error rate, typically it's a few percent. It won't affect your key rate at all. So that's why normally, if you choose so many discrete phases, normally you directly ignore this effect. So that's why we don't really go into this kind of finite analysis for this discrete phase because the effect is too small. That's the reason.
Mm-hmm. Okay, so you don't take into account that imperfection in the security proof.
Oh, we do.
Because it's small.
Yeah, it's too small because I'm talking about that still, okay? Because when you consider this deviation, you need the deviation will introduce more phase error rate. Your original phase error rate is already a few %, but this extra phase error rate is only like a 10 to the 10 to minus 20,
Okay.
10 to minus 10. It won't affect the final key rate. That's why normally people just ignore it directly.
Thank you.
Hello, thanks for the talk. Give us a lot of details about the modern parry. I have a question. Can you predict that what is the longest distance that a modern parry can reach in the future? Because I in my idea, in the longer distance fiber, there will be more loss. So it's harder to make the modern parry. Yeah.
That's true. That's true. So basically, like when the distance is getting longer and longer, so when I first click, I wait for the second click, it will be longer and longer. Eventually, it's too long. That's the distance too long. Then I have a lot of fluctuations. You're right. So now what we are trying to do is that keep in mind that the intensity is higher. So that means that if you compare to the previous like a twin field QED, it's hard to say in the long distance which one is better. But you're right, the key point there is still the sifting factor. So that's the problem we try to solve for the long distance. Otherwise, if we can solve that one in terms of distance, I think more pairing should go to the furthest distance for this kind of protocols. Yeah.
Okay, thank you very much. Thanks to the speaker again, please.
All right, thank you. Thank you.